You're building an adaptive AI system for collaborative learning. The goal is simple: detect when students are confused, frustrated, or engaged and intervene. But here's the problem. In co-situated collaboration, there is no gold standard for ground truth. Physiological sensors disrupt the interaction. Log data is too sparse. And discourse? It's masked by social dynamics. So how do you model the internal affective states of a group without breaking the flow? A recent study by Anindo, Venkatecha, Akampaw, and Blanchard tackles this head-on. They move beyond static emotion detection and use ordered network analysis to map the temporal structure of epistemic emotions during collaborative problem solving. If you're working on educational AI, affective computing, or learning analytics, this paper offers a blueprint for handling coarse-grained, retrospective data without losing the temporal signal. Let's start with the setup. The researchers recruited 27 participants, organized into 9 groups of 3. They tackled the weights task, a physical collaborative problem where groups use a balance scale to infer the relative weights of 5 blocks. After the task, they used retrospective cued recall, or RCR. Participants watched a video of their session and reported their affective states at specific moments. Crucially, reports were captured in 2 ways: self-caught, where the participant initiated the report, and probe-caught, triggered after 60 seconds of inactivity. Now here is the technical bottleneck. RCR data is temporally coarse. It's not a continuous stream like a heart rate monitor. It's a sequence of discrete reports. Most researchers default to descriptive summaries, treating emotions as independent frequencies. But that destroys the sequential information. The authors argue that even with coarse granularity, the order of reports contains quantifiable structure. To unlock this, they apply ordered network analysis, or ONA. For those familiar with epistemic network analysis, ENA, you know it models co-occurrence within windows. ONA extends this by enforcing temporal order. The authors use a moving window of 2 events. If a student reports curious, followed by confused, the model creates a directed edge from curious to confused. These edges are aggregated across the group, normalized for reporting frequency, and then subjected to singular value decomposition. SVD reduces the high-dimensional transition matrix into orthogonal dimensions that maximize variance. The result is a 2D projection where nodes represent emotions, edges represent transition strengths, and node size indicates self-transition persistence. A large node means that emotion tends to linger. The student stays in that state across successive reports. So what does the network look like? Across all groups, there is a stable epistemic core. Curiosity, optimism, and confusion are tightly linked. They show strong bidirectional transitions and robust self-loops. This suggests that during collaboration, affective experience is characterized by short-range persistence rather than rapid, random switching. Confusion and curiosity often sustain each other, which aligns with control value theory. Emotions arise from perceptions of control and value, and in this context, the core cluster drives sustained sense-making. The horizontal dimension of the network separates states associated with forward progress, curiosity, optimism, surprise, from those linked to difficulty and struggle, like confusion, conflict, and frustration. The vertical dimension is trickier, hinting at a distinction between active struggle and disengagement, but it's not perfectly clean. Let's dig into the group dynamics by comparing faster and slower groups. The authors split the groups by median task duration. The difference network reveals a stark contrast. Faster groups exhibit ordered structures centered on curiosity and optimism. They show strong transitions between these states, and while disengagement appears, it's peripheral and fleeting. This suggests smoother coordination and reduced affective friction. Slower groups tell a different story. Their networks are dominated by strong bidirectional transitions between confusion, conflict, and frustration. Specifically, the transition from confused to conflicted is significantly stronger in slower groups. This implies that slower groups aren't just taking more time, they are trapped in a different affective topology. They experience sustained epistemic struggle that bleeds into social conflict. The authors note a caveat. Faster groups might also reflect a dynamic where 1 or 2 members drive the task while others disengage, but the affective structure points to reduced conflict-driven friction. The paper also isolates the impact of the reporting mechanism. Because of a class imbalance, the authors built separate ONA models for self-caught and probe-caught reports. The shapes diverge. Probe-caught reports, which occur after silence, show much stronger self-loops in the core states. This makes intuitive sense. If you're probed because you're quiet, you're likely still in that state. The network stretches because these persistent states are sampled repeatedly. Self-caught reports, however, show a more distributed structure with stronger connections to high arousal states like conflict, frustration, and surprise. Self-initiated reports seem to capture moments of perceived affective change or spikes in arousal, whereas probe-caught reports capture the sampling of ongoing, stable states. This is a critical methodological insight. The way you harvest data fundamentally alters the network topology you observe. What are the implications for AI systems? First, adaptive interventions cannot rely on summary statistics or isolated emotion triggers. The data shows that confusion is part of a productive core with curiosity. But in slower groups, confusion transitions into conflict. Your AI needs to monitor local trajectories. Is the student moving from confusion to curiosity? That's productive struggle. Confusion to conflict. That requires intervention. Second, when designing data collection, you must account for how reporting mechanisms bias the structure. If you only use probes, you'll overestimate persistence and miss the transitions. If you only use self-reports, you might oversample high arousal shifts. A few limitations to keep in mind. The sample is small, with a male skew and fixed labels. RCR is susceptible to recall bias. And since all groups solved the task, we don't know how these affective structures correlate with learning outcomes. But as a baseline for applying ONA to retrospective data in collaboration, this work is solid. Ultimately, this research pushes us to view affect in collaboration as a dynamic, ordered system. The sequence of emotions matters as much as their presence. Faster groups flow through curiosity and optimism. Slower groups grind through conflict and frustration. And the lens through which we measure this changes the map we draw. For anyone building the next generation of affect-aware educational technologies, the message is clear. Model the sequence, respect the temporal structure, and remember that not all confusion is created equal.